So, let us continue with the 26th lecture in this course on process control, analysis, design and assessment, and the last lecture on the mini series of lectures on Nyquist stability criterion that we have been talking about. So, in the last two lectures I talked about the S plane, the f of S plane, and how you convert contours in S plane into an f of S plane. And we also looked at a very interesting result which said if you draw a contour in the S plane and if you encircle a certain amount of zeros and poles of f of S inside the contour, and then as you move along the contour you keep tracking how f of S changes, and that is a very simple thing because once you have S value you can simply compute f of S and plot it in the f of S plane. And if you track that and then you finally look at the f of S plane contour and then count the number of encirclements around the origin, then the number of encirclements will give you z minus p, where z is the number of zeros inside your closed contour in the S plane and p is the number of poles of f of S inside the closed contour in the S plane. Okay. So, that is a very interesting and remarkable result which we can use for analyzing stability of time delay systems. Now, there are lots of mathematical arguments and so on why this is true, and there are things that you need to do to draw this contour, such as excluding the poles or zeros on the S plane contour itself and so on, but those are complications which we will not really focus on in this course because this is the first introduction to this idea. Nonetheless, what I want you to realize is while doing this, while I showed you examples where we wrote the f of S as a numerator by denominator polynomial, I showed you because we are just computing f of S for different S and doing nothing else, the numerator and denominator could have the e power minus tau ds term. So, that simply does not create any problem at all because for any S I can compute e power minus tau ds. So, ultimately this e power minus tau ds term, whether it comes in the numerator or denominator with other polynomial terms, for every S on the contour on the S plane you can simply compute this f of S. Okay. And once I tell you that whatever result that we saw is also true even if you have this e power minus tau ds terms, then it clearly says now that we have a way to analyze the stability of time delay systems. That is a connection that I want you to realize. Now, I also towards the end of the last lecture showed you how these results are useful for closed loop systems, where I said we want to cover the whole right of plane to ensure that there are no zeros of 1 plus GC in the right of plane. So, I said what we do is we start on the imaginary axis at minus j infinity and then keep traversing the imaginary axis all the way up to j infinity, and then we take a long circular route covering all of RHP and then come back to minus j infinity. And this you can imagine just in your head that this is a clockwise movement in the S plane, and you might think about how am I going to compute all of this, right. So, there are programs that will do this and you do not have to do anything in terms of a computation. So, in your labs that go with this you will see these Nyquist plots. What you really need to do is have the ability to interpret them, and interpreting these plots simply means computing or calculating number of encirclements around an origin in the f of S plane plot. So, if there is some software code which gives you this contour in the f of S plane, all you need to do is really look at that and then be able to count the number of encirclements and use this idea of n equal to z minus p to do whatever you want. So, that is the important thing to keep in mind. Okay. Now, we will come back to the way in which we are going to use this in control. We have already seen this picture here. This is how we convert this notion of closed contour to cover the whole of RHP, right of plane is completely covered when I take a contour where I start moving from minus j infinity all the way up to j infinity and then go on the circular route. Now, let us go back and then understand each of these bullet points, so that the transition, the general result to control is very clear. I am not going to reiterate the fact that this can be done for e power minus tau ds also, because I have already said this many times. All I need is an f of s function. For any s I can compute f of s. Okay. So, we have already subsumed this idea of doing this for time delay systems in all the discussions we have had till now. So, let us look at each one of these bullet points and then see whether we understand this carefully. So, first, if we assume that the process itself is stable, then GC will have no poles in RHP. Okay. So, let us see whether we understand this. So, let us look at G, okay, which itself is some numerator by denominator. C is also some numerator by denominator. Clearly, we are not going to design controllers which are unstable. So, we are assuming that there are no poles of the controller in the right of plane, and if the process is stable, then D of s is also not going to have any poles in the right of plane. So, GC, which is some numerator, let us say, by denominator, when I put these together, will have no poles in the right of plane. Okay. So, if the process is stable, GC is not going to have any poles in the right of plane. Okay. So, this is something that we should understand. Now, the second thing is, if GC is N1s over D1s, basically D1s is the polynomial, denominator polynomial, from which you compute all the poles. Okay. Now, look at what will happen if I have 1 plus GC. Okay. So, 1 plus GC will be 1 plus N1s by D1s. Okay. So, this is going to be D1s plus N1s by D1s. Okay. So, if you look at GC and 1 plus GC, the poles of GC and the poles of 1 plus GC are the same. Okay. So, that is the first bullet point. So, basically what it says is, if you assume the process is stable, then GC will have no poles in the RHP. Okay. That is from this notion here, and when you actually write 1 plus GC, you write 1 plus N1s by D1s, which is D1s plus N1s by D1s. So, the poles of GC and 1 plus GC are the same. Okay. So, this is the first bullet point which we have to understand. Now, the next bullet point basically takes this idea to this Nyquist plot, and the f of s that we are going to use to plot all of this is going to be 1 plus GC, and now this 1 plus GC has some zeros and poles. Okay. So, now let us look at 1 plus GC, and then as we go along this very long infinite path, right, starting from minus j infinity all the way up to j infinity and go on the circular route covering all of RHP, we want to ask whether this f of s, which is 1 plus GC, because we are going to draw this Nyquist plot for 1 plus GC initially, and then we will refine it further. So, when we look at this f of s as 1 plus GC, so we are doing this plot here, and then we are going to get a corresponding plot here. Now, within this, will this f of s have any poles in the RHP? If you ask that question, now the answer is it will not have any poles in the RHP if this process is stable. Why? Because if the process is stable, we already said GC has no poles in the RHP, and the poles of 1 plus GC and GC are the same, and since GC has no poles in RHP, 1 plus GC cannot also have any poles in RHP, right. So, within this big circle, by looking at the encirclements, we already know we can see the difference between Z minus P. Okay. But as I said before, we cannot individually compute Z and P, but in this case, if the process is stable, we can guarantee that this P is 0 for 1 plus GC, right. Okay. So, why is P is 0 for 1 plus GC? Because poles of 1 plus GC are the poles of GC, and G is stable, controller will choose it to be stable. So, we will have no poles. Okay. So, for stable systems, then when I look at this contour like this, when I go from minus j infinity to plus j infinity and all the way through a large circular path, then when I look at these encirclements, if the process is stable and the f of s that I am considering is 1 plus GC, poles are 0. So, the result is n is z. So, the number of clockwise encirclements will be equal to the zeros of 1 plus GC. This is the most important and interesting result from a control viewpoint. So, basically what this says then is that if I have, let us say, one clockwise encirclement of 1 plus GC, right. So, that basically means Z equal to 1. So, within this large contour, this 1 plus GC has at least one 0 is what it would mean if I see a clockwise encirclement around origin in the Nyquist plot. So, that would mean then the closed loop is unstable. Why is the closed loop unstable? Because we already said GC by 1 plus GC, okay, and if I take this GC as some numerator by denominator, 1 plus GC will be D1S plus N1S by D1S. Okay. So, this and this will get cancelled. Now, the denominator of GC by 1 plus GC will be the numerator of 1 plus GC. So, any 0 of 1 plus GC will become a pole of GC by 1 plus GC. So, if I have one encirclement, that means there is one pole for 1 plus GC, one 0 for 1 plus GC in the RHP, which becomes a pole for GC by 1 plus GC in RHP, which makes the system unstable. So, basically what we have done is we have reduced the identification of stability to simply counting the number of clockwise encirclements of 1 plus GC around origin. Okay, that is a beautiful and simple result here. So, this then says if there are no clockwise encirclements of the origin in the f of s plane, which is 1 plus GC, then there are no zeros of 1 plus GC in RHP, because no clockwise encirclements will mean n equal to 0. We already know p is 0, n is equal to z minus p. So, this is 0, this is 0. So, this has to be 0. So, no zeros of 1 plus GC in RHP, that means no poles of GC by 1 plus GC in RHP. So, remarkably, by just looking at this f of s plot or the Nyquist plot, we are now able to guarantee that you might have infinite expansion polynomial in the denominator because of your e power minus tau ds and so on, but we are going to guarantee that that is going to have no 0 in RHP. That means you might have infinite number of zeros, but I am still guaranteeing that nothing will be in RHP by just doing this contour plot without actually ever computing the poles or zeros of the transfer functions. So, that is the most interesting and beautiful idea here, right. So, all I am saying is you simply get this plot, look at the clockwise encirclements around origin. If there are no clockwise encirclements around origin, that means your closed loop is stable, okay. And there will be as many clockwise encirclements around origin as there are zeros in the right half plane for 1 plus GC, right. So, if 1 plus GC has 3 zeros, then I will have 3 clockwise encirclements, because n equal to 3 minus p is 0 already, because we know the system is stable. So, that is how this whole idea of Nyquist stability is translated to time delay systems, and it is translated to time delay systems because f of s can be any functional form. I need to simply compute the f of s value as I go through this contour, and this is done using software, and you will basically have these plots which we have to interpret. So, if you understand each one of these points clearly, and I have explained this here, then basically you understand how to use this Nyquist plots for stability. Now, just a point, if you know that there are no encirclements, clockwise encirclements, then you know that the system is stable, and this result is true for processes that are stable. But I do not want you to think that this result is restricted to analyzing stable processes. A simple extension is, supposing you know that your process is unstable and you know that your open loop process has, let us say, 2 poles in RHP. Okay. So, let us take that case. Just wanted to kind of explain to you how this result extends to unstable processes also. Supposing you know that there are 2 poles of your process in RHP. Okay. Now, when will I say, once I design a controller, the closed loop system is stable? Okay. Now, you do not have to change anything. This result you are going to use to understand this. So, we know n is z minus p, and when I look at 1 plus GC, we have already said the poles of GC and 1 plus GC are the same. So, if there are 2 poles of GC in RHP from this fact, then there has to be 2 poles of 1 plus GC also in RHP. Okay. So, when I do this infinite contour, for stable systems I put P equal to 0, for unstable systems I have to put P equal to as many poles in the RHP as there are in your process transfer function, open loop process transfer function. So, if I know that there are 2 poles in the RHP, then P is 2. So, I have N equal to Z minus P, which is Z minus 2. Now, if the system is stable, then what will happen is Z has to be 0, that means I have to see 2 anti-clockwise or counterclockwise encirclements around the origin. So, if N is minus 2, so for your closed loop system, as you plot this 1 plus GC, if you look at the plot and then you find that there are 2 counterclockwise or anti-clockwise encirclements of origin, then N is minus 2. So, this will be Z minus 2 Z. So, there are no zeros of 1 plus GC, which means the closed loop is stable, right. So, the open loop is unstable with 2 poles, and if you design a controller in such a way that your Nyquist plot shows 2 anti-clockwise or counterclockwise encirclements of origin, then that basically means that there are no zeros for 1 plus GC in RHP, which is what is critical for closed loop stability. So, this is how you use the same result to analyze closed loop stability of unstable systems. Okay. So, now the last bit of result that we are going to use is the following. This is summary or restatement of whatever we have seen. For a closed loop to be stable, okay, basically Z has to be 0. Z is the number of zeros of 1 plus GC in RHP, and the number of zeros of 1 plus GC in RHP will give you the number of the closed loop transfer function in RHP. So, as long as that is 0, the closed loop transfer function does not have any poles in RHP. So, from the rule N equal to Z minus P, if Z is 0, N equal to minus P. Okay. So, whenever Z is 0, N will be minus P. So, if I have as many counterclockwise encirclements of the origin as there are unstable open loop poles, then the system is stable. So, that is the main result, because that comes from N equal to minus P. If I have 3 open loop unstable poles, I should have 3 anti-clockwise or counterclockwise encirclements, and similarly if I have 1, I should have 1, and so on. So, this is the result which basically generalizes this for stable and unstable processes. Now, if the open loop is stable, then P is 0, N should also be 0, there should be no encirclements. Now, one last thing, whenever these plots are given, since we are interested in 1 plus GC, we were looking at encirclements around origin are 0, but typically the plots, what they do is they do not plot 1 plus GC, f of s not as 1 plus GC, typically the plots are for GC. So, if you want to get GC from 1 plus GC, you have to subtract 1 here. So, whatever is an encirclement around 0, when I plot for GC, I have to look for 0 minus 1. So, I have to look for encirclements around minus 1 and 0 in GC plot. Okay. So, till now we have just been talking about looking at encirclements around origin, because f of s we were considering as 1 plus GC, but for sake of convenience what people do is they do this Nyquist plots not for 1 plus GC, GC. So, all I am saying here is if you want to go from 1 plus GC to GC, you have to subtract 1 from 1 plus GC. So, if you are looking for zeros encirclement around the origin in the 1 plus GC plot, because to go from 1 plus GC to GC I have to subtract 1. Similarly, the 0 would move to minus 1 0. So, basically you look for encirclements around minus 1 0. Okay. So, that is all the final differences, because this is how most people report the Nyquist plot in control systems. So, I hope this is clear. This is just where you look for encirclements, nothing more. Okay. So, in summary, we said whenever I have GC by 1 plus GC, typically we have been saying this is some numerator by denominator, and then you can look at the stability of the systems by looking at the poles of D of S, and if I can get it in root resolved form, then I can use partial fractions. Then we talked about root stability table when I do not write it in root resolve form, and then when we came to time delay systems we got into this issue of this term having e power minus tau ds in its functional form. Then we said we have to look at some way of handling this. That is where we came up with this notion of Nyquist stability, where the key idea is if I have an S plane and I am doing encirclements around something in the S plane, I am looking at how it is going to look like in f of S plane, the same encirclement, and we got this result which said that the number of encirclements of origin in f of S plane n is z minus b, where z is the number of zeros of f of S within the contour that is used in the S plane, and p is the number of poles of f of S within the contour that is used in the S plane. Then we went to the next idea, which is to say make this f of S 1 plus gc, and we know the number of poles of gc and number of poles of 1 plus gc are the same. So, we are looking at only the zeros of 1 plus gc because it comes in the denominator. So, by making this f of S 1 plus gc, we came up with the result saying the number of clockwise encirclements around origin is z minus p, but now the S plane contour is something that we take which is from minus j infinity all the way up to j infinity and this long. So, this encompasses the all of RHP. So, if we are able to show that this 1 plus gc has no zeros in the RHP, then we are able to show that the closed loop is stable. So, that is what the idea that we used, and basically I said you do not have to worry about doing these computations because these computations are done using a software. You need to only learn to interpret these computations and look at pictures and be able to understand it. The last idea we said was whenever we are looking at encirclements for f of S, if it is 1 plus gc we look for encirclements around 0, if it is gc we look for encirclements around minus 1 0. So, this is 0 0 basically because we are talking about a complex number. So, there has to be a real part and imaginary part. Okay. So, basically if you are looking for encirclements around here, which is the 0 0 point for 1 plus gc, because when we do gc we have to subtract minus 1 from everything. So, we have to look for encirclements around minus 1 0 when we look at gc. Okay. So, that basically finishes this whole idea of Nyquist stability and how Nyquist stability can be used for understanding the stability of time delay systems. So, with this we finish the portion on designing controllers, understanding controllers and analyzing the stability of controllers for time delay systems. In the next lecture I will talk about the next difficult dynamics, which is actually when the process is open loop unstable, how do we design controllers, how do we design robust controllers using direct synthesis approach. I will see you in the next class. Thank you.